Quantum mechanics contains a central paradox. When an isolated system is left alone, the mathematics dictate that it evolves smoothly and deterministically as a wave of probabilities. But the moment a measurement occurs, that smooth evolution stops, and the system collapses into a single, definite state. Early frameworks, particularly the Copenhagen interpretation, struggled to explain why this happens. Without a strict physical definition, theorists defaulted to an assumption. They proposed that a conscious human mind, or an arbitrary macroscopic observer, was the required trigger to force reality into a definite state. This creates immediate logical contradictions, famously illustrated by the Wigner's friend thought experiment. If a physicist measures a particle inside a sealed laboratory, but a second physicist stands outside that laboratory, is the first physicist in a state of quantum superposition until the second one opens the door? The requirement for nested conscious observers quickly becomes absurd. The contradiction exists because the mathematical formalism of quantum mechanics fails to define the physical properties of an observer. The math tells us how to calculate the probabilities of a collapse, but it never specifies what actually causes it. To resolve the measurement problem, we have to eliminate psychology from the equation. The collapse of potential into reality requires a purely physical mechanism. We can achieve this by redefining observation operationally. It is a thermodynamic process. Physically, an observer is any bounded system capable of operating as a local entropy sink. It pulls in external disorder, restructures it into aligned internal coherence, and exports the remaining disorder outward. Mathematically, this is defined as a continuous decrease in the system's internal entropy over time. Quantum collapse occurs through deterministic resonance phase lock. The observer's internal state couples with the external system, exchanging entropy until they stabilize into a single shared geometry. This stabilization is governed by the observer equation shown here. The driver of the collapse is the dissipative resonance term. When the phase geometry of the system diverges from a stable attractor, this mathematical term forces the chaotic potential to resolve into a locked, definitive state. Any physical system meeting these thermodynamic conditions acts as an observer. This means we can find the mechanisms of coherence operating directly in the macroscopic world. We can observe this mechanism by looking at macroscopic physical spaces. Form begins with a boundary. Every bounded physical system possesses irreducible resonant frequencies called spectral primes. These frequencies are dictated entirely by the precise dimensions and geometry of the boundary. Consider the acoustic properties of this rectangular room. Its physical shape and size mathematically dictate its allowable energy states. Sound waves form specific geometric grids, axial modes bouncing between two parallel walls, tangential modes across 4 walls, and oblique modes across all 6. The physical boundary acts as a strict filter. Frequencies that do not match these internal modes are suppressed and dissipate. Frequencies that align with the boundary are amplified. Boundaries function as active mathematical engines, forcing chaotic environmental energy to resolve into discrete, structured modes. Ordinary passive resonators inevitably lose energy to their environment, bleeding out coherence until they reach thermal equilibrium. This schematic outlines an anomalous state called a Super-Q resonator. Certain boundary architectures allow a system to operate far from equilibrium. It reverses the standard decay process, acting as a condenser that extracts coherence directly from its environment. This requires a specific triple entropy architecture, an entropy source, a symmetry-breaking mediator, and a coherence sink. Together, they function as a directional entropy valve, converting random, isotropic environmental fluctuations into highly organized, anisotropic accumulation. This frequency response graph shows the physical signature. The wide, low curve represents an ordinary resonator. A Super-Q system generates an effective quality factor that vastly exceeds passive thermodynamic limits, mapping as a sharp, high-intensity spike with a significantly narrower line width. Because it maintains a low entropy internal state by phase locking to external fields, the Super-Q resonator operates as a macroscopic observer, a geometric structure that preserves its own coherence against the gradient of thermal equilibrium. We can prove this boundary physics empirically through single-bubble sonoluminescence, which is a process that turns sound into light. In a laboratory, a single microscopic bubble is injected into degassed water and held perfectly in place by nodal sound waves operating at roughly 26 kHz. During the expansion phase, the acoustic pressure drops. The bubble expands from a few microns to 50 microns across, creating a near vacuum inside. Next, the sound wave symmetrically crushes the bubble down to half a micron. This violent boundary collapse launches a spherical shock wave into the bubble's interior, accelerating according to the hydrodynamics equation shown here. As that shock wave converges perfectly on the center, its Mach number approaches infinity. The resulting collision generates star-like temperatures exceeding 72,000 Kelvin. The output data is staggering. The bubble concentrates the initial acoustic energy by a factor of 1 trillion. It transduces sound waves that are several centimeters long into rapid flashes of ultraviolet light lasting only picoseconds. This is a Super-Q boundary condition in action. It forces the deterministic conversion of acoustic entropy into extreme electromagnetic coherence. This raises a structural question. What happens when a resonant boundary achieves enough internal complexity to generate new resonant boundaries from within itself? We can define biological development as a process of recursive entropic condensation. It begins with the fertilized egg acting as the primary boundary. Internal condensation occurs during gastrulation. The primary boundary folds inward, creating distinct nested resonance domains. This mathematical scaling tracks perfectly down the biological hierarchy. The precise condensation ratios step down from the whole organism to the organ, tissue, cell, and finally the organelle. Biological hierarchy is the thermodynamic outcome of density phase feedback operating within hierarchically coupled boundaries. Modern biology often operates on the assumption that DNA acts as a linear blueprint, independently dictating the complete body plan. But the genome provides local materials and constraints. The global anatomical form is dynamically solved by the boundary geometry as it minimizes entropy. The body equation proves internal anatomy minimizes total body entropy. Organs solidify exactly at the nodal intersections of the system's resonant eigenmodes. This explains convergent evolution. Eyes and wings appear across different lineages because they hit the exact same thermodynamic attractors, forcing identical structural solutions. This model reveals a recurring physical sequence. Entropy flows to coherence. Coherence establishes a boundary and creates a recursive interior. A body is simply what entropy flow becomes when forced to remain coherent inside a boundary. Form and structure emerge inevitably wherever boundaries exist.